Hello everyone, this is Pawan Patil, working as assistant professor in the Department of Electrical Engineering, SITCOE. So now we are going to discuss about power electronics, the topic cycloconverters. So what is a cycloconverter and all that details we will be finding in this lecture. And in this lecture we are going to discuss about the single phase cycloconverter and the three phase cycloconverter. ठीक है. Before going for the in detail working and analysis of cycloconverter, let us see what is the use of a cycloconverter. It is also nothing but a AC to AC converter. So in the previous my video I have discussed about AC to AC converter in the waveform point of view. There I have shown you that how the wave shape of the waveform can be changed, but here we are not going to change the wave shape particularly. Our main aim here is to change the frequency of the device. So this is very important. This is the only device in which we can convert AC to AC with change in frequency. We have other methods also to convert DC and all, but without conversion, if you want to convert the frequency of a system, then we have to go for the cycloconverter. So if you once again discuss about AC to AC converters, transformer is a AC to AC converter, then AC voltage controllers are also the AC to AC converter, and the cycloconverter is also a AC to AC converter. Okay, so come on and we'll discuss about the single phase cycloconverter. So this circuit shows the operation and the circuit of the single phase cycloconverter. Here we do have a transformer. Obviously it has a primary side and the secondary side, and from the secondary side we have taken the center tap, such that obviously the center tap means the voltage over here will be equal to the voltage in the second region also. Okay, so now we have connected the load to the output, or you can say the load like this, in this manner. So one thing is, this voltage, the first voltage, will be applied to the load through this circuit, and the second voltage is applied to the load through this circuit. So two circuits we have combined. So these are nothing but the anti-parallel connected SCRs. Okay? And we have named it as P1, N1, P2, N2. Why it is not that P1, P2 and N1, N2, that we will discuss in detail. Okay? And coming back to the circuit again. Here, consider the first positive half cycle of the input supply. So how the input is flowing? It is positive sinusoidal waveform. In the first positive half cycle, that is over here, in that case, the upper voltage, this is positive, this is negative, and this is positive, this is negative. Okay? And in this case, for the upper circuit, we can have P1 as forward biased and N1 is reverse biased, because its cathode is connected to positive. And here we do have N2 forward biased and P2 reverse biased. Okay? Now we can have two output voltages. Either we can have a negative voltage or we can have a positive voltage. If we want to have a positive voltage, then we have to turn on P1 by giving the gate supply, or if you want the negative supply, for the same instant, don't give the gate supply to P1, instead give the gate supply to N2, so that negative voltage will be applied across the load. So using this we can get alternate positive and negative half cycles. Okay? So let us decrease the frequency. For that, what we do is, in the first positive half cycle, P1 is forward biased. So when P1 is turned on, in that case I will be getting a voltage, this side positive, this side negative. So let me have this kind of waveform I will be getting. Okay? In the next half cycle what happens? The sign of these waveforms changes. So this becomes negative, this becomes positive, this becomes negative, and this becomes positive. In this case, P2 is forward biased and P1 is reverse biased, and N1 is forward biased, N2 is reverse biased. Similarly. Okay? Now again, if you want positive half cycle, we have to turn on P2. If you want negative half cycle, we have to turn on N1. Now what I do is, I turn on P2 by giving the gate supply to P2. So what kind of waveform I will be getting? I will be getting one more positive waveform like this. Okay. So this is, in this way we can have positive continuous cycles by turning on P1 and P2 continuously. Okay. Suppose we require the negative half cycles. In that case, we have to go for turning on and turning off of N1 and N2. So consider the same case again. When the input is positive, this is positive negative, this is positive negative. In this case, which is forward biased? P1 is forward biased and N2 is forward biased. Now what I do is I just turn on N2. When I turn on N2, across the load, negative voltage will be appearing. Okay. Again in the next cycle, again the signs are going to change. Here this becomes negative, this becomes positive, this becomes negative, this becomes positive. In this case, N1 is forward biased. Now when I turn on N1, again I will be getting a negative voltage across the output. Okay. So in this way I will be getting the outputs. Okay. So this is nothing but what is the output which you are getting for a continuous sinusoidal waveform. So here two positive cycles, two negative cycles. Here P1 is on, here P2 is on, here N1 is on, here N2 is on. Sorry, N2 is on and here N1 is on. So using this, we can have alternate continuous positive cycles and continuous negative cycles. So now what happens? We have an average of one positive cycle here, average of one negative cycle here. Because of this, the total frequency of the circuit is going to change. So let us see how the waveform is. In that case, this is the output voltage waveforms. Okay. So this is the input, positive, negative, positive, negative, positive, negative, like this. Here I have got here I have got totally three waveforms, three positive cycles and three negative cycles. So as discussed earlier, here which is turned on, here it is P1, here it is P2, again P1 here. So we are getting three continuous positive cycles, and here it is, if it is P1, here it should be N1, N2 and N1. So we are going to get the negative half cycles. So what is the total frequency? Earlier the total cycle was from here to here. Now this is your positive cycle and this is your negative cycle. So I have increased the time 3 times. If I increase the time 3 times frequency, then what should be the frequency? If time is increased by 3 times, frequency should be decreased by 3 times. That is, we know that T is equal to 1 upon F. If I increase the time by 3 times, the frequency should be decreased by 3 times. So because of that, we are getting 1/3 of the frequency which you are getting earlier. Consider it is a 50 Hz frequency. Now how much is the frequency? 50 divided by 3. That much frequency you are going to get at this waveform. So this is the working of the single phase cycloconverter. Okay. Now we'll go for the next one, and again, and this is the case whenever resistive load is there. Okay. And one more thing is, here we can see whatever the output is there, in that we can control the firing angle also. Means along with frequency we can change the output voltage also in case of single phase cycloconverter. Okay. So the firing angle you can vary from 0 to 180 degrees. So when I increase the firing angle, the output voltage decreases. Okay. And by doing alternate positive and negative cycles, or changing the number of cycles in the positive and negative cycle, we can change the frequency also. Okay. And this is the thing with respect to the resistive load. But suppose we do have a inductive load also. In that case, as we know, the waveform is going for the little bit of negative side. That is the case in case of inductive loads. So what happens to the current then? The current, when the device is turned on, the current increases. Then the device is turned off, the current starts decreasing and it goes to 0. The next cycle again, the current increases, decreases, increases, decreases, like this. Why the current is increasing like this? It should be following the same waveform? No, it is not going to follow the same waveform, because we are having an inductive load, and the inductor will not allow the current to increase like this. It will make the current to increase in the exponential manner, and after that the current decreases, increases and decreases in the exponential manner only. Okay? So, or you can say some delayed manner. In this way we are going to get the output for this thing. So what is the frequency for this one? If this is the normal operating frequency, how much frequency I have reduced, or how much time I have increased? I have increased the times by 4 times. Because of that, frequency is going to be decreased by 4 times. Okay? Here again P1 P2 P1 P2 N2 N1 N2 N1. In this way we are going to trigger these things. Okay? So this is about the single phase cycloconverter. Now we'll discuss about the single phase cycloconverter in the bridge manner. So this is one more kind of circuit. So that circuit was simple, and this circuit is operationally complicated, but since it is not having any transformer or something, it is little bit cheaper compared to that, but the complexity is more. Why the complexity is more? Because we are going to use 4 thyristors. So what circuit is this? If you say only this one, that is, if you say only half of this, it looks like a rectifier circuit, and if you see this half, it looks like a inverter circuit. Okay? So using this we can get positive voltage and currents. Using this I can get negative voltage and currents. It means to say, if you turn on P1 and P4 and P2 and P3, we will be getting continuous positive cycles, and if you turn on N1 N4 N1 N4 and N2 and N3, we will be getting continuous negative cycles, and in the similar way we will be getting the waveforms. If you want positive cycles, turn on the first converter or use bridge 1. If you want negative cycles, use bridge 2. In this way it is going to work. Fine. Next we will be going for the 3-phase cycloconverter. So this is the circuit of a 3-phase cycloconverter. So this indicates the block diagram, and this indicates the circuit diagram. Okay? So what does the circuit diagram indicates? In the circuit diagram we are having 3 phases, A, B and C. In each phase I have provided the thyristors T1, T2, T3. These thyristors work for only positive cycles, and these 3 thyristors give you the negative cycle, or this is called as positive group and this is called as negative group. And as in the earlier case, it is going to provide, the positive group is going to provide you the positive cycles, negative group is going to provide you negative cycle, and overall you will be getting a frequency like this, or you can say the voltage with reduced frequency. Okay? And one more thing we can have here, that is Ig. Okay? It is used to reduce or remove the circulating current from the device. So what do you mean by circulating current? It is one of the important concepts. Circulating current is whenever this is used for positive cycles and this is used for negative cycle, in that case, and whenever both are connected, means to provide positive cycle it is connected, to provide negative cycle it is connected, then the voltage at this limb and voltage at this limb, maybe they are equal in amplitude, but the thing is there might be little bit of instantaneous voltage difference between them. Because of that, a current will flow from here to here, or it will flow from here to here, which will never go to the load. So that current which is circulating among these phases is called as the circulating current. Okay? So what is the disadvantage of circulating current? If circulating current is there, obviously losses are going to be increased, and it is going to reduce the efficiency of the total circuit, and along with that it is going to harm the devices, because the devices are loaded to a greater value. Okay? So for that purpose circulating current has to be removed. So to do that we are going to use this inductor. It is called as Ig, the reactor. Using this reactor we can reduce the circulating current among the devices. Okay? So this is, which kind of cycloconverter is this? We are having an input of 3-phase and output is single phase. So this is a 3-phase to single phase cycloconverter. ठीक है. Now we'll go for the next waveforms. So what kind of waveform we will be getting? So this is the waveform which we are going to get using the cycloconverter. ठीक है. We'll go for this. Here we are having continuous three phases. Particularly we are going to work on the line voltages only. Line voltage means line to line voltages. Initially, if you provide higher what you can say firing angle, in that case the device will not turn on earlier. It will take some time. So after some time, after this becomes this one, then it turns on like this one. After some time, it is going to turn on. Now go on reducing the firing angle. So it starts and then it starts like this. So after this instant, go on increasing the firing angle so that the firing angle goes on increasing and the wave shape becomes like this. Okay? So this is for the positive cycle. Okay? If you want the negative cycle, then again we have to use either negative converter or the negative circuit. For example, in this case we are going to use this one. What is that? 1 minute. In this case we are going to use this circuit for the negative cycles. When you do that, we will be getting negative cycles by using this. Here also, first go on reducing the firing angle, the voltage increases, then go on decreasing the firing angle, the voltage decreases. Maybe you are getting continuous waveforms like this, like voltage decreases, then it decreases like this. We are getting the waveform like this. Overall, when you find out, the wave shape will look like an AC waveform. So that is what is shown over here. So in this way, we can get a three-phase to single-phase cycloconverter operation. Okay? Now we'll go for three-phase to three-phase operation. In three-phase to three-phase operation, nothing much to be explained because we have seen this circuit just now. Using this, I have done for a single phase. Now repeat them for second one, repeat the same for the third one. Using this, we can get the three-phase waveforms. Okay? And this is output voltage waveforms. So what the output voltage waveforms indicates? Again, here we are going to generate the waveforms like this using continuous turning on and turning off of the devices only, obviously. Okay? So that's wave shape. And if you want to generate a three-phase waveform, in that case, each phase will be shifted by 120 degrees. The third one will be shifted again by 120 degrees. So how can you achieve the 120 degree phase shift? It again depends on how we are going to fire the thyristors. So when you fire the thyristors in a proper manner, we can get one phase as R, other phase shifted by 120 degrees, the other phase shifted by again 120 degrees. So we will be getting a three-phase waveform from this one. Okay? Thank you. पॉज करते थे, पॉज केलं होतं मी.